Another way you can use the tables of electrode standard reduction potential is to work out what's going to be a good oxidizing agent and what's going to be a good reducing agent. So for example, if you look at the reaction I have at the top of the slide, fluorine against 2 electrons that produce the 2 fluoride anions, that standard reduction potential is plus 2.87 volts. So it's not only a positive number, it's a large number. That means fluorine undergoes that reaction easily. It means the reduction reaction is very favorable. It has a very large voltage. It has a strong tendency to accept 2 electrons and become the fluoride anion. So that is going to be a very good oxidizing agent. Remember, the difference between talking about oxidation and reduction and oxidizing and reducing agent is that oxidation and reduction talks about what the element goes, what reaction is happening to it, gaining or losing electrons. Oxidizing and reducing agent is about what that element or that compound can do to the other compounds. So fluorine has a strong tendency to reduce, to gain 2 electrons. It's a very good oxidizing agent. It will have a very strong tendency to accept electrons from other species. You have in the slide the example of lithium. If you look at the electron potential, reduction electron potential for lithium plus, to gain 1 electron and become lithium solid is minus 3.05. So it's extremely negative. Not only that reaction is not spontaneous, is that you have to have an incredibly good compound donating that had an incredible tendency to release electrons for lithium to be able to accept them. However, if you think of the reaction going the other way, lithium in solid state to produce lithium aqueous plus 1 electron, that electrode potential of this oxidation reaction would be plus 3.05. So going the other way, the reaction is perfectly and really nicely spontaneous. So lithium has a very strong tendency to oxidize, to liberate an electron. So lithium solid will be an excellent reducing agent. So you not only can work out if a particular pair of hard reactions is going to give you a galvanic cell or electrolytic cell, if it will liberate if it will happen spontaneously producing electricity, or it will be an electrolytic cell, you will need to provide that amount of electricity, that voltage, for the reaction to happen. It also allows you to work out what's going to be a good oxidizing agent, so it's going to have a very strong tendency to reduce, or a good reducing agent. It's going to have a very strong tendency to oxidize. Let's have a little chat about the oxidation state of carbon and how you can work out if, when a reaction has happened, carbon has oxidized or reduced in an organic compound. Although you can use oxidation states, you can always use oxidation states. It's usually faster and easier to follow the amount of oxygen, the number of bonds your carbon has with oxygen, to work out how oxidized that carbon is. So let's think of the simplest compound you can have with only 1 carbon. This compound is called methane. And let's say that your carbon now has 1 bond with an oxygen and the other ones are hydrogens. Or your carbon has 2 bonds with an oxygen. This is the compound methanal or methanaldehyde, or formol, you might have heard that name. Or your compound has even more bonds with oxygens. That's methanoic acid or formic acid. Or your carbon has as many bonds of oxygen with oxygen as it can master. So this is the side of the most oxidized species, and this is the most reduced species. So when you have a compound with carbon and undergoes a reaction, and the reaction means that your carbon has gained bonds with the oxygen, this is an oxidation. So your compound that carbon has undergone an oxidation. So what you have used an oxidizing agent, there will be another hard reaction of something that has undergone a reaction. So the more bonds with oxygen that carbon has, the most oxidized that species will be. And the fewer bonds with oxygen it has, the more bonds with hydrogen or other carbons it has, the more reduced that species will be. And just very briefly, not all reactions, not all biological reactions which are redox reactions actually involve carbon or oxygen for that matter. So for example, here we've got nitrogen fixation by nitrogen fixating bacteria, which works in anaerobic conditions, and you have the bacteria are able to take nitrogen from the air and hydrogen ions from the water present and produce ammonia. And that is an example of a reduction reaction. You have nitrogen here, which is an oxidation state 0. And if you make the oxidation state of this nitrogen here, it's an oxidation state of -3. How can you transfer electrons in a biological reaction, in a biological system? Well, there are several routes. You can transfer them directly as electrons in a straightforward redox reaction, in which, for example, here you've got iron 2+ and copper 2+, and the iron 2+ becomes iron 3+, so it has lost one electron, and that electron has gone to the copper 2+, that has gained an electron to produce copper+. You can transfer them as hydrogen ions. If you keep track of the oxidation states of these imaginary atoms A and B, it's not boron, just a compound atom B, you would have hydrogen here has an oxidation state of +1, and you have 2 of them. So the oxidation state of A on this compound would be -2, and this would be 0, it's not interacting with anything. This one would be 0 for A. And here again, the hydrogen is an spectator ion, nothing happens to it, has an oxidation state of +1. B would be -2. So that's an example of a redox reaction that happens and hydrogen ions are involved. You can also transfer you can also transfer electrons as a hydrate anion. So the H-, and the electron is in that hydrate ion. It's a hydrogen that has 1 proton and 2 electrons. Or there can be an electron transfer, although you cannot see it because there are no charges, so it seems like, oh, nothing has happened, through a combination of an organic compound with an oxygen-containing compound, either oxygen or water or any compound that contains oxygen. And I gave you an example of this in a previous slide. For example, you have the compound ethylene or ethene, and you make it react with oxygen-containing compound, let's say water, and you produce ethanol. Let's put the H here. And that's an example of an oxidation. So there has been an electron transfer. This is an oxidation, so another compound, an oxidizing agent must have reduced, so must have provided those electrons for this reaction to happen. Even if you cannot see it as charges, those electrons are still being transferred. Lots of examples of redox reactions in biological processes and key processes. The process of respiration, burning glucose with oxygen to produce CO2 and water and energy. That's an example of an oxidation reaction. Photosynthesis, you take CO2 and mix it with water. Plants take CO2 and water and light and produce glucose and dioxygen. That's a reduction. The example of nitrogen fixing bacteria, they take nitrogen from the air, they take hydrogen or hydrogen ions from the water, and they produce ammonia. The process of protein folding and oxidation reduction process occurring with proteins. For example, I don't think they can be seen here in yellow. Disulfide bonds. The fact that you can have sulfur bonds, disulfide bonds in between your molecule, or you can have them broken as SH. So reduction going this way, oxidation going this way, and those sulfide bonds that can be broken and made that is through a redox reaction. There are many and very important redox reactions that happen in biological systems, and there are only a few universal electron carriers. And I've brought here a couple of examples. You probably have seen more in your biochemistry modules. The first example I'm bringing here is NAD, nicotinamide adenine dinucleotide. And this is normally involved in oxidation process. This is the full structure of NAD. And this is just a blow up of this. This one is a blow up of this particular section. Look what's happened here. When a substrate undergoes an oxidation, it gives up 2 hydrogen atoms. And those 2 hydrogen atoms, one is going to go to the NAD plus as an hydride, as an H minus. So this hydride anion will be an H minus. And then what this H minus is going to do is going to join here, move this double bond here, and move these electrons from that pair to compensate that positive charge. And that is how you get this compound, NADH. The other one will be released as a proton. And this is another example of a biological electron carrier. And this one is NADP is typically involved in reduction reactions. And nicotinamide adenine dinucleotide phosphate. The phosphate is this one here. So when a substrate is oxidized, it will give up 2 hydrogen ions. One will go to the NAD plus to create NADPH. And if you look at the structure of this section here and how it looks, here in this carbon you only have 1 hydrogen, and this is where your that hydride anion is going to enter. This is definitely beyond the scope of these videos, but I thought that you may be interested in what happens in the reaction. So the hydride goes to this carbon, it moves this double bond here, and this double bond goes to compensate that positive charge which disappears in the product in NADPH. So one of them is passed to the NADP plus as a hydride, as an H minus again, to make NADPH, and the other one is released as a hydrogen ion, as a proton to the medium.